All right, welcome to today's lesson. We're starting a unit on solutions. We're going to do a variety of different things with solutions, pretty much get to the point of figuring out how strong they are, how weak they are, what kinds of things dissolve and what kinds of things don't dissolve. And in the end, we're going to figure out how solutions interact with one another in terms of making precipitations and in terms of acid-base reactions, because acids and bases are usually solutions. So we're going to start off with basics here today, kind of a review of some topics about what the components of a solution are, and then kind of talk about how things dissolve is kind of probably the newer part of today. So here we go. In terms of solutions, you guys have already learned about this, I'm assuming, at some point in time. The basic definition that a solution is a heterogeneous mixture. It's made of at least two things, and those two things are mixed together so thoroughly that you can't even see the individual components anymore. They're basically mixed at the molecular level. The two components have names to them. There's a solute and a solvent, and it's important to kind of know which one's which. Typically we think of a solution as being like a solid dissolved in a liquid, but that doesn't always have to be the case. So by definition, the solvent is the component that's present in greater quantities, the stuff you got more of. A solute is the other stuff, or it could be more than one solute even, like think about Gatorade. You've got a variety of things dissolved in there. So the solute is the other components of the mixture that's present in lesser quantities. So solvents are the things that do the dissolving, and then solutes are the things that are going away. You put it in there and it looks like it's gone. Magic, right? After a few minutes of stirring or whatever you got to do. So solute and solvent, and then the final mixture of the two together is called a solution. So solution, solute, and solvent. Between these two kinds of things, again, I'll remind you that there is the most common version of it, which is what we call our aqueous solutions, right? Something dissolved in water. We've got all kinds of things that can dissolve in water, but the most common things that people think about is like taking salt and dissolving in water, or some other chemical and dissolving in water. And that's a really common version of a solution. So the solute would be the solid, the sugar, the salt, the whatever, and the solvent would be the water in this case. But there's other kinds of solutions as well. Less common, but when you start to think about it, they're all over the place. So for example, you can have a liquid dissolved in another liquid. So for example, if you go up to one of those big soda machines that you go and put your cup, the fountain machine, right? So you've got a solution of water, and then you have another solution of syrup. And so it's basically a little bit of syrup dissolved in a bunch of water, some carbonation, makes a delicious beverage of some sort. So a liquid dissolved in a liquid. You can have a gas dissolved in a liquid. That's what carbonation is in sodas as well. So you've got to have carbon dioxide dissolved in the liquid, which is the solvent, to make it bubbly. You can also have a gas dissolved in another gas. Air, believe it or not, is a solution. It's a homogeneous mixture of nitrogen gas, oxygen gas, some carbon dioxide, some water vapor, some farts. There's a variety of things that's up in there. So the solvent is the thing that's present in greater amount. So the solvent in air is actually nitrogen gas, 80%. And oxygen gas, or the water vapor, whatever, would be the solutes that are present in that particular mixture. One of the trickiest ones is something called an alloy, which is a solid dissolved in another solid. Now, I don't want you to think this happens at the solid state. Usually this is two things that were melted together and then solidified later. But things like brass and bronze are alloys. Steel is another one, which is an alloy, where, for example, steel, you've got the solvent of iron, and then you have some solutes of things like chromium or aluminum or other things that are melted into that steel, into that iron, basically, to make a new kind of solution. And once you solidify it, you basically have this weird looking ice cube, brick of metal anyway, that's an alloy, which is a solid solution. So again, just a couple of other types of examples that you can have, and there's others as well. But again, the most common type we deal with is a solid solute dissolved in a liquid solvent. There we go. So how does this work? It's kind of a crazy process at the molecular level, and we've got to start thinking kind of at that molecular size. A couple of the things in your notebook ask you to draw molecular level drawings. It's like this picture that's on the screen when I'm referring to molecular level. What's actually happened atom by atom, not just like, oh, there's a block and now it's gone. It's got to actually have little atoms and dots and circles and things like that. So this little diagram here kind of shows about what's happening in the solvation of salt. So there's the green and bluish stuff in the center is supposed to be like salt crystals. And then the little tiny dudes around the outside are our little water polar bears that are around there. So the little water molecules are surrounding the solute. This is kind of our process. Over here in this left diagram, the water molecules are the little red and blue guys. And again, you've heard me talk about them being polar bears, but it's these little bears that are sort of floating around. So that's the first step, is that the water molecules have to surround the solute. The second thing is that these water molecules are actually attracted to the ions within the salt. So they kind of stick to it. It's impossible to touch water without getting wet. It's kind of a weird thought. So as soon as you drop those solute molecules in there, they're surrounded by water, and the water just goes literally and kind of attacks, not really attacks, it's friendlier than that, but touches it. And then the third thing that happens is kind of being pictured over on the right, is that the ions, the water molecules, are sort of towing individual ions out away from the main block of salt. So for example, up here you can see there's a chloride ion right here that's been surrounded by some friendly little polar bears, and it's sort of being towed out into the solution, like come join the party. Down here you have the same kind of thing happening with these sodium, not just the chlorine, it's the sodium as well, and they're sort of getting plucked off and sort of pulled away. And so this is the process of solvation. Solvation is the name for dissolving something. It's the noun form of that. What's important to realize is at the end, that after a while, all of these different ions are going to move away from that center block. That center block will get smaller and smaller and smaller. The ions will go away. And ions individually are too small to see. The block, or the salt crystals, or the grains, whatever, are easy to see because they're large. But those individual ions are so tiny that they literally just blend in. Light passes right through them and we don't see them anymore. So even though at the beginning we can see the salt chunk in here and we've got clear water surrounding it, as this process goes, these ions are going to diffuse out into the remainder of the water. And remember, the water is present in a much larger percentage than the salt. Eventually, they will simply, to us, look like they disappear. They're still there. They're just too small to see with the naked eye. And again, they're going to spread out through the process of diffusion. So when we take a look at this at a closer level, we have to kind of understand a little bit about how this works when we're talking about ionic compounds. Key idea here is that water is a polar molecule. I refer to it as polar bears all the time. What that means is that the water molecule itself is a little bit unbalanced, that between these two, and you can kind of see these little funky shapes, these little weird looking things. This is actually a lowercase Greek letter that you don't have to worry about too much. But what we find is that every single water molecule, the electrons tend to spend more time on this side of the water molecule, the oxygen side, and they tend to spend less side on the hydrogen side because the oxygen's more electronegative and we've got some unshared pairs over there. That side ends up being partially negative, and that's what that little goofy looking snake-like letter looks like. It's a lowercase delta, by the way, if you look it up. But that's what that means, that this side of the water molecule is partially negative. The hydrogen side of the water molecule is partially positive. It's not true charges like an ion, it's just sort of an unequal sharing kind of thing is what's going on here. And so these polar molecules will then surround the ions facing the directions that match or are opposite, I guess, to the polarity of the ion. So if you've got a negatively charged ion, the water molecules will orient so that their positive poles are facing it. And so all their little ears are going to be facing towards the chloride ion. And then the opposite thing is going to happen with the sodium ions. The sodium ions are positive, so all the negatively charged sides of those polar molecules will be facing towards it that way. So they're kind of reverse one another. And this idea that water molecules are polar, that they have these slight partial positive and negative sides, is actually what allows them to attract to the strongly positive and negative charges of the ions. And that's what allows ionic compounds to dissolve, usually pretty easily, in water, for example. So again, you can kind of see what that picture is. Again, it's related to this concept of polarity, and that's why I always refer to water molecules as being our little polar bears. Kind of makes sense. I know it's a bad joke. So anyway, with these, as we move forward to this, water is incredibly important to us. As living creatures on a planet that's covered 75% water, your body is more than 75% water. Most of our chemistry in our world, especially our organic chemistry, is based on water. So the fact that water is polar and a polar solvent is actually really important to us as living things and into chemistry in general for all of us. So for example, we know that any solute that has any sort of a charged region to it. It can be fully charged like ionic compounds, or it can be partially charged like polar compounds. Those things can all pretty much dissolve in water. There's a few exceptions to that I'll get to a little bit later on. But that means that water, we kind of call it the universal solvent. So many things can dissolve in water that it makes chemistry actually a lot easier on our planet. Water kind of lubricates things, I guess, and makes it a little bit faster. Nonpolar things, not so much, and we'll get to that here on this next slide. You know that there are certain things that simply don't dissolve in water, right? Oil and water don't mix. So why is that? You know that if you put oil into water, it'll simply float on top. Certain types of things will just sink to the bottom perhaps, but in this case, you'll get this layer, and no matter how much you shake it up, oil will not dissolve in there. And this comes down to the fact that oils, fats, and all kinds of things like that, are a different class of compounds called nonpolar compounds. The bonds within these things tend to be so evenly distributed that overall the molecule itself has no charged regions at all, not even partially charged regions. There's no even like hint of positive, hint of negative. And because of that, that water molecule wants to stick to something with a charge, and if you've got something with no charge to it, they simply don't connect. And again, so this is a non-polar sort of thing. And again, it's a lot like polar things trying to stick to, or like magnets trying to stick to plastic, or wood, or something along those lines. By the way, plastic is actually a non-polar compound, most plastics, which is why plastics don't dissolve in water and they don't break down over time. And again, they're not magnetic either, but different idea. So one of the things we do have to worry about a little bit, and we've talked about this in lab, is that lots of organic solvents are what we call nonpolar. So things like paint thinner, turpentine, gasoline, acetone, some other things like that can act like nonpolar stuff. And there's some really dangerous things out there called hexane and toluene and some other things. And I don't want to use those in lab because they're kind of dangerous for us, but they're around. But anyway, organic solvents. So oil and water don't mix because oil is nonpolar and water is polar, and they just don't stick to each other. So this comes to the main idea here, that when we get to solubility or solvation, the idea that like dissolves like. If you have polar solvents, and water is the most important polar solvent for us, polar solvents will dissolve things that are either ionic or things that are polar, that are partially charged. Nonpolar solvents are simply going to not do anything with them. They'll sit on top or sink to the bottom, but you cannot get them to mix together, and that's kind of what's going on here in this picture on the left. If you have a nonpolar solvent like oil, it will be able to dissolve other solutes that are also nonpolar, and those will dissolve in there just fine, but things that are polar or ionic will not be able to dissolve in those. And again, you can see those when we do things like put salt in oil. Salt in water is fine because salt is ionic and water is polar, they will dissolve. But if you put salt, which is ionic, in oil, which is nonpolar, they simply don't combine. The salt just sinks to the bottom and sits there, just doesn't do much. So this picture over here on the left, you've got some colored water because the water coloring itself, the food coloring, is polar. And then you've got the water, which is polar, versus the oil, which is not colored because it's nonpolar. So like dissolves like. In terms of why all this thing happens, this comes down to an idea of force, intermolecular and intramolecular forces. The forces within atoms, molecules, and the forces between different molecules. And this really kind of is the picture of why some things dissolve and why some things don't. Like, why do precipitates form? Why do they not form? Some of these things. And there's three basic ways that things can attract to one another, three different variations. So you can have, in statement number one there, particles of solute and particles of solvent. Do they like each other or not? Number two would be particles of the solute to themselves, so sort of within the salt crystal or within the precipitate. And number three is retraction within the solvent itself. So water molecules like to stick to other water molecules, or oil molecules like to stick to other molecules. So basically the way this comes down is if the attraction to the solvent is greater than the attraction within the solute, it will dissolve. Again, if the water molecules, the solvents, can pull those things apart, then it will dissolve. So if number one, the attraction between the solute and the solvent is greater, then the things will come apart and the thing will dissolve. On the other hand, sometimes things don't dissolve correctly. So when you have a precipitation reaction, for example, and you're forming a solid, that means that the particles of the solute are so strongly attracted to one another that the water simply cannot pull them apart, and you have a solid that forms the precipitation. Between oil and vinegar, you've got two different things where they're so deeply involved in each other, the oil is attracted to the oil and the vinegar is attracted to the vinegar, that they simply do not combine with one another, and so that the intermolecular forces are just not strong enough to overcome the intramolecular forces. So again, just another way to kind of think about what's happening inside solutions when things are dissolving, or not dissolving, I guess, at the atomic or molecular level. So here's our review from what we did today. So the basics, here's our polar bear, right? Solutions are heterogeneous mixtures that are combined of at least two different things. We've got solutes that dissolve in solvents. The solvents are present in the bigger quantity. The solutes are present in a much smaller quantity. The name of the process of dissolving is called solvation, when something is pulled apart and it kind of gone down to its atomic or mini molecular size, so we can't see it anymore. Water is our universal solvent, not quite universal. Obviously, it doesn't dissolve nonpolar things, but it's our kind of universal solvent. And the reason why that works is because it's a polar molecule. It's got a partially charged side, that's positive, the hydrogen side, and it's got a partially negatively charged side, which is the oxygen side, and that allows it to pull lots and lots of things into solution. We talked about the process of like dissolves like, that things with charges will dissolve other things with charges, and things without charges will dissolve other things without charges, so that's kind of easy. So polar solvents will dissolve things that are either polar or ionic. If you've got a nonpolar solvent like oil, it will only dissolve other things that are also nonpolar in nature. Finally, we kind of mentioned briefly that idea of intermolecular forces. It's kind of a tug of war. Do the things want to attach to each other, or do they want to get pulled apart? And that's kind of a way to interpret what's going on at the atomic level between these different things. So there you go. Hope you've enjoyed this kind of review and kind of like an in-depth kind of look at what's going on in your solvation. Our poor polar bear. I think he's going to dissolve. Very sad. Have a good day.